Hey class, good afternoon. So let us now proceed to the topic uh, in review. Okay, so in mechanical engineering review. So this is fans and blower. So actually class, this topic is also topic in industrial plant engineering. Okay, so you can use this topic fans and blower in industrial plant engineering also class. Okay. For those who are not graduating yet, of course, you can use this in industrial plant engineering. Okay, so here is class the definition of fan. Okay, so it's a machine used to apply power to a gas to increase its energy content, thereby causing it to flow or move. Okay, that is fan. For blower, it's a fan used to force air under pressure, which means resistance to gas flow is imposed upon discharge. Okay? And exhauster is a fan used to withdraw air under pressure, which means resistance to gas flow is imposed upon the suction. Okay, so the common uses class of fans. Okay, so basically, so ventilation, air conditioning system, okay, force and induced drop service for boilers, okay, dust collection, drying and cooling of materials, and then cooling towers, heating mine tunnels, ventilation, pneumatic conveying, and other industrial processes, okay. So those are the common uses class of fans, okay. So we have here the basic difference, okay, according to ASME. So pump, a machine which adds energy to a liquid, and fan is a machine which adds energy to a fluid at a pressure rise equal to below 1 psi gauge. Okay, take note class. Okay, below 1 psi gauge. Blower, okay, so a machine which add energy to a fluid at a pressure rise between 50 and 1 psi G. Okay, zero point 0.5 to 1 psi rather. And then compressor, so a machine which add energy to fluid at a pressure rise above 50 psi gauge. Okay. So basic elements of fan, of course, the wheel or the impeller. And then, of course, that is the rotating member, housing or the stationary member. Okay. And then we have here the types of fan. We have here the propeller type, the tube axial type, and the bin axial type. And the at the below, of course, is the centrifugal type. Okay. So we have here the types of blades and performance curves. Okay. So we have here. So backward, inclined. So we have the straight, forward curve, and then at the bottom, of course, the CFM versus the power uh, diagram. Okay. So function of fans, okay, is to move air or gases through distribution system and apparatus required for conditioning of buildings. Okay, for drying and cooling, for pneumatic conveying, dust collection. So this was already mentioned a while ago. So factors affecting fan selection. We have here quantity of gas to be moved per unit time, estimated resistance, and expected variations, amount of noise permitted, space available for the fan, economic implications, and so on and so forth. Okay? So, fan performance class. Okay? So, fan capacity Q. Okay? So, volume handled by a fan expressed in cubic meter per second at the fan outlet condition. So, this is basically class Q equals to area. Cross-sectional area of the duct, okay? Where the air passes through and the velocity, of course, of the air. So, basic equation. Okay, next, we have here the static pressure. Okay, so the static pressure head. So, class, the head, of course, is only composed of two types. Okay, so one is, of course, the static pressure head. So, which is you can easily determine. So, static head is equals to head of water. So, the head of water class can be obtained from the manometer reading. Okay? So, if there is a manometer installed in the installation of fans or a blower, so you can easily identify that height of water. and then substitute that here in this equation, multiplied by the density of water. So divided by the density of air. Okay, so density of air class can be determined using only the formula PV equals to MRT, or the mass over volume equals to density, or density equals to P over RT. Okay? So take note class, we have here the standard condition. So the standard pressure is 101.325 or 29.92 inches of mercury, or that is 21.1 degrees Celsius. And the density class of standard air condition is equals to 1.2 kilogram per cubic meter. And for the density of water, we have 9.81 kilonewton per cubic meter, 1,000 kilogram per cubic meter, or we have 9.81 kilonewton here, and 62.4 pound per cubic foot. Okay? So take note class of the constant. So this is very useful in calculating problems involving fans. Okay? So, and then try to memorize the constants. Okay? Next is the velocity head. Okay? So, velocity head corresponds to the average velocity determination. Okay? So, from the volume of airflow at the fan outlet. So, velocity head equals to the square root of, or the square of the velocity divided by 2 multiplied by the gravitational acceleration. Okay? So, velocity head now is in terms of feet, meters, or whatsoever. Okay? So, the total pressure head class now is equals to the summation. Okay? The H total is equal to the static head plus the velocity head. Okay? So, very easy class. So, determining the power, that is same as with the power and determining the, or for a pump. Okay? So, power is equals to the density, okay, multiplied by the total head, multiplied by the total discharge. Okay? So, we have also here, in fans and blower, we have the so-called static air power. Okay? Wherein, the head that you are going to use in this power is only the static head. Okay? So, density of air multiplied by the discharge multiplied by the static head. So, take note class, this topic is very easy. Okay? So, next is the static efficiency. Okay? So, the static efficiency, of course, the static air power divided by the shaft power. Take note class that in determining the static power, you are only going to use the static head. Okay? So, another is mechanical efficiency, that is equals to the power output divided by the shaft power. Okay? So, very easy class. Okay, so we have also here using the Bernoulli's equation. Okay, so applied to fans. Okay, so the total head now is equals to, in terms of pressure and velocity only. Okay, so the pressure, so the change in pressure between the outlet and of course the inlet, plus the change in velocity square of the outlet and the inlet divided by 2g. Okay, so these are now class D equation. Or simply, that is the density of water multiplied by the change in height. So that is the headwater at point 2 and headwater at 1 divided by density of air plus B square, or the B sub 2 square minus B sub 1 square over 2G. Okay, so that is Bernoulli's equation applied to fans. Okay, so where of course, again, P sub 1 and H sub 1 is the negative if below atmospheric pressure. Okay, so P1 and it's W1 and let's static pressure reading. Okay, P sub 2 and it's W2 discharge pressure reading. Okay, density of water, density of air, inlet velocity, outlet velocity, and the gravitational acceleration. Okay, so we have here class the pan characteristics. Okay, and pan law. So this is class quite complicated. Okay, so but anyway, so this can be easily applied. So by just memorizing this formula. Okay, so the relation between the discharge and the diameter and speed of the pan. Okay? Discharge 2 is equals to discharge 1 multiplied by the ratio of the diameter, of course, at 2 and 1 cube multiplied by the ratio of the speed. For the head, so that is h 2 is equals to h1 d2 over d1 square and 2 over n1 square multiplied by the density 2 over density 1. Take note, class, if the density maybe or the diameter of the impeller is not will not change, of course you can eliminate this d here, the ratio of d. If the density also do not vary or does not vary, you can also eliminate this. Okay? Take note of that, class. You can eliminate those parameters who will not change or there is no change from the initial to the final condition. Okay, so for the pressure, so that is P sub 2 is equal to P sub 1 d2 over d1 to the fifth. Okay, n2 over n1 cube and then density 2 over density 1. So take note, for pan efficiency equal. So take note, class. So look at the condition. Okay, so do not use this equation if the condition is not uh, the same or not telling you to use the parameters. Okay? Next is for variable pan speed. Okay? So, constant pan size and constant density. Q sub 2 also Q sub 1 and 2 over N1. Okay? So, H2 equals to H1. So, that is N2 over N1 raised to 2. And for power, power 2 is equals to power 1 equals to N2 over N1 raised to 3. Take note, class. This is for similar pans. Okay? Similar pans. Selecting similar pans but different in sizes. Okay? Take note of that, class. Okay. So, variable pan size. Okay? So, Q sub 2 over Q sub 1 is equals to Q sub 1 equals to D sub 2 over D sub 1 cube. H sub 2 is equals to H sub 1. And for power, that is equals to P2 over, is equals to P1 D2 over D1 raised to 2. Okay? So, variable gas or air density. So, okay? So, constant pan size and speed, constant system or points of ratings. Q2 equals to Q sub 1. H2 equals to H sub 1. So, density 2 over density 1. So, take note, class, that the speed is eliminated here because the speed is now constant here. Okay? And then for P sub 2, that is equals to P sub 1, density 2 over density 1. So, another for pan combination, pan in series. Okay? So, if class, the installation of pans are in series, so Q sub 2 is equals to Q sub 1. Whatever is the discharge passing through 2 shall also be equal to the discharge at or passing through the first fan. Okay? So but the head, of course, will increase twice. Okay? So will be doubled. Okay? So not actually doubled, but if the pan capacity, of course, are the same, the head total will be doubled. Okay? Another is pans in parallel. Take note that the if pans is installed in parallel, the head that the air was delivered, of course, will not change. But the discharge, of course, will be doubled. Okay? Thank you very much, class. So, wait for the next presentation of this because I will give you the example of the discussion in this topic, class. Thank you very much.